So I'm going to be talking about large language models. It's in two parts. And there's foundations this morning, and then the second part is going to be like research frontiers. So like just a tiny bit about me. I was at DeepMind for about 4 years. So I've kind of been there for the transition from the way to build artificial general intelligence is to do like reinforcement learning in simulated environments, to the way to build artificial general intelligence is to train large language models. And hopefully I can give you some of the kind of the intuitions that people have about why these things are powerful and why this kind of paradigm has changed. But that does also mean that I've been in that sort of large language models are everything environment for a little while. So I've tried to kind of step back to foundations. If I haven't stepped back successfully, then just say like, what does that mean? So yeah, what am I trying to achieve today? I'm trying to explain the transformer architecture. So that's like the algorithms, like literally how does self-attention work? What are all the components? So you should be able to, by the end of this, like at least be perhaps 80% of the way to being able to say, sit down in a collab and write yourself, sit down with a collab or a Jupyter notebook and write yourself a transformer. And also the intuition and philosophy behind why we do this. And then you should also have the kind of background by the end of this talk to kind of make sense of this afternoon's talk. But there's a sort of general point that I want to say as well, which is that although we're building these things, at least in my opinion, they're quite impressive, we actually know really very little about the things that we're building. We can build them, we can look at them, but it's kind of like an alien has landed on Earth. And I feel very curious about this thing. And so this is kind of an incredible time in my view. This is essentially AI for science, but I think that potentially there's kind of a new science that's being born now, which is like the science of AI. So really, I think it's like, from an engineering perspective, it might be a bit alarming that we don't know very much about the things that we're building and the things that we're deploying. But from a scientific perspective, it's quite exciting. You know, it's sort of like a new frontier has opened up. And yeah, to go on to questions policy, like just so you can do what you like, but I think it will run best if we have, I've got about 45 minutes of material. I think it will run best if you ask clarifying questions like throughout. I'm aiming for you to understand this. If you don't understand it, it's my fault. Please ask me clarifying questions. And then broader questions like, what is this? What is this term that I read on Twitter? What does that mean? I'll try and answer it. Or like, if you have a question that is more of a comment about your own research, I also want to hear about that. And I'll upload slides and share them. Please nag me if I don't. Right. So on with the talk proper. I'm going to start with the intuition. Like, why are LLMs a thing that you might even want to build in the first place? Like, why is this something you want to do? And you might say, well, LLMs are a really silly way to solve a lot of problems. Like, it was fine when we were building single-purpose machine learning systems. And I think the thing you really need to understand for the question of why are people building large language models, it's because they want to build artificial general intelligence. They're not kidding. Like, they're first and foremost a thing that's designed to build a general intelligence, and then they turn out to be useful for a whole lot of economically valuable things, kind of by virtue of being allegedly a step on the way towards general intelligence. So if you're saying, if the kind of question comes to mind, wouldn't it be better to train a single purpose system to do X? The answer is often yes, it would. But from the perspective of the people who are training language models, that doesn't actually get them very much further along. And so there's this sort of shift in view that took place over the last 4 or 5 years in terms of how, what the sort of pathway to AGI is. And this has moved from kind of, we do a single task, which is sufficiently rich. So like maybe we do Go, and this kind of teaches us stuff that we learn from doing Go. We learn kind of algorithms that are useful and can be generalized to more complicated domains and so on. And then this sort of shifted to, so those of you who are topologists might sort of have encountered the topological potato representing a topological space. This is the task space potato. So this is just like all the tasks that you might want to specify. It's not a very well-defined notion, but people draw this a lot on blackboards and whiteboards a lot. So we used to start one, and then we be like, oh, we'll do multiple tasks. We'll play all the Atari games, and they're sort of somewhat separate. And then there's this idea that, well, what we'll do is actually we'll do clusters of tasks, and we're going to hope for sort of interpolation between these tasks. And if we're really lucky, we might get some generalization to neighboring tasks. And large language models sort of represent a shift to going like, why don't we just try and do literally everything? We won't try and do any of it particularly well, but we will try and do as much as we possibly can. And this kind of comes in parallel with a change in perspective from like what's really important in AI is rich embodiment, reinforcement learning from scratch. It's sort of this idea that you have a little guy who goes around in a simulated environment and does tasks of ever increasing complexity, to completely abandoning embodiment, switching over to supervised learning and kind of just maximizing the use of human data. So this is the sort of perspective shift that I think has really taken place over the last 4 or 5 years in AI. Now, if we want to actually turn this perspective shift into actions, then what sort of domains have the property that they don't necessarily need embodiment? You can do some supervised learning, and you're just going to go all out on the data. You want data that's extremely diverse, easy to collect, and very information dense. And language has the useful benefit that it has all of these properties. Like you might realistically expect that you could spin up a bunch of web scrapers and collect a meaningful fraction of everything that humanity has written on the internet and just put it on some hard drives, and you don't even need very many hard drives. So that's kind of not something that would be the case for most other domains. And language has a bunch of other additional benefits. It's adjacent to all sorts of other stuff like code and like things like Lean for theorem proving and that kind of thing. It's easy to interact with. If you had to interact with ChatGPT by videos, for instance, it would just be much harder to kind of interact with. Okay, so that's sort of why the kind of reason that people have moved in this direction. I think the reason that people are interested in building general intelligences have generally shifted from reinforcement learning in simulated 3D environments to language models, but make them bigger. This would be much less persuasive if it doesn't work. So why might it work? Well, there's a few things. One intuition is just basically accepting that deep learning works. And this is perhaps a somewhat unpopular viewpoint. I think probably in reality, you need to temper it a little bit. But I think, it's a good first cut. Like deep learning basically works if you have a big enough data set. That doesn't just mean like, in terms of I've got like a million or a billion or a trillion data points. It means they're also sufficiently diverse. It's no use having the same data point like a million times. You've got a big enough data set, a big enough model, and enough compute to train the data set on the model, then you'll probably get out solutions that they generalize well. The next thing is the idea that scaling works. So as we scale our models, they generally get better, and they get better in a way that's sort of worthwhile. I'll go into scaling later today. And perhaps the biggest shift is the idea that just prediction causes understanding. So we used to think that we had to train models, and we had to like really force the understanding into them, that what they would learn would generally be a kind of magical nonsense. Like we really had to force the things to learn sensible concepts, or to learn like representations that actually represented, that actually like corresponded in some meaningful way to the structure of the data. And this idea that like simple prediction tasks actually cause quite a lot of understanding to emerge. I think this is an empirical finding that's taken quite a lot of time to settle in. And again, like the idea that deep learning works, it's probably like 90% correct. But you can certainly find examples where it doesn't work. So to make this a bit more concrete, consider the string like 2 + 2 =, and you try and predict the next token or the next word. Well, what does 2 + 2 =? 2 + 2 = 4, except, so first of all, if you have a lot of data like this, you have x + y = for all sorts of values of x and y. Eventually, you'll learn a generalizing algorithm for adding x and y. You won't just memorize a number of values in the data set. But as an example of this sort of super multitask setting, and the kind of things that you end up needing to learn if you just take the whole internet and jam it in, there's lots of strings where 2 + 2 is not followed by equals, is not followed by 4. It's quite reasonable in some cases to say 2 + 2 = 5. And that might, when you have the string 2 + 2 = 5, it's often kind of prepended by something like, either it's an example of like synergy, or it's an example of someone saying something totally nonsensical, and someone saying, oh, that's like saying 2 + 2 = 5. So when you take an enormous data set, you get all this kind of richness and variation, and trying to do next token prediction on it can be quite can force it to learn quite surprising things. And you can also expect that if you do next token prediction, you can gain kind of conceptual knowledge. Like imagine trying to complete the string, the capital of France is, well, it's Paris. So if you have, again, a corpus that's about the real world, like if you put Wikipedia in there plus some other stuff, you will end up learning a lot of facts in order to accurately complete the string. And underpinning this is the idea of positive transfer. So we have one datum, and things we learn from that datum help us out on a bunch of other data. Okay. Yeah.
So conceptually, right? So I appreciate this picture as well. But I'm just wondering, so if I want to, use deep learning to solve a specific problem, right? Is there like a recommendation, like, I guess we talked about Go, but I guess in science we have a lot of problems. And do you think it pays off to use this, foundation models to solve a specific problem that you want to really solve very well, right?
Depends on exactly how you're trying to solve the problem. You might be trying to solve the problem getting grant money. Yes, in that case, you should definitely say foundation models. But no, a serious answer to your question is, you can imagine this in a couple of ways. One is to simply say, no, probably not. You just do not use foundation models. They're very hyped, but perhaps you won't have the kind of enormous scale data set that you would need. Like it's really mind-bogglingly huge. Another perhaps more constructive approach would be to imagine kind of trying to dissolve the specific problem that you're trying to solve as and what I mean by that is if you think about your data set in terms of, like, to go back to the potato, you've got a point in this potato. What else is nearby? What is it like? What is your data set a specific example of? How can I collect the most amount of data on that and train? And what's the sort of self-supervised training that I can apply on that? So that's one way of. And what can I do to get the most individual examples out of each datum, which is often corresponds to some sort of self-supervised task in a way that will hopefully make more sense when I talk about the architecture.
Maybe just, I mean, of course, maybe you kind of say it, but I guess is the trend in industry that, I guess, we use the deep learning for, molecule discovery, right? To play Go, I don't know, to predict weather. Is the trend that everything is going to be replaced by a foundational model? Or?
Do you mind if we pump that to the end?
Yeah, sure.
I'll write it down and then we'll come back to that at the end. Yeah. Okay, so this is the kind of nitty-gritty bit. This is where things start to get a bit more down to earth. So an overview of the transformer architecture. I'm going to go through this bit by bit. The first thing is, how do we get from these strings? We've decided that we want to train by next token prediction. We want to do it on natural language, but we want to do deep learning as well because we think it works. So we've got this phenomenon. How do we turn this into kind of vector representation that deep learning works with? The answer is tokenization and embedding. I'll explain what these are. Pipeline language model. That's essentially two states. We split the text into tokens. I'll explain what a token is in a second. After we've done a bit of pre-processing on, which is hence removing all sorts of formatting errors, or in the old days it used to be converting strip and punctuation. We don't do that now because that stuff actually carries a lot of useful semantic information. But the sort of pre-processing and normalization step consists of taking a large data set and in some way making it into like better quality text. So split into tokens, and then we embed those tokens into a vector space. I'll talk about tokenization first. What tokenization is the process of taking a string, and splitting it into sort of discrete subword components. Now, why do we want to do this? The reason that we want to do this is we could imagine going character by character, and that would be fine, but it would be tremendously computationally inefficient. If we have to run a transformer for every single character, then the amount of text we can fit in a transformer, for reasons we'll come to in a bit, would just be minuscule. We'd have tiny strings. The task of predicting one character from the preceding like 1,000 characters is much less interesting than predicting one word from the preceding 1,000 words. There's just a lot more richness in that text. So we train a tokenizer, and I'm not really going to go into the details of how you train tokenizers because it's not really that active a research area. But a tokenizer is a thing that will scan along your input string and split it into chunks. And these chunks have been kind of determined by the process of training your tokenizer, which you can think of as like finding the most frequent substrings. So here, for instance, I've completely invented this tokenizer, splits the string tokenize me into, I've got 3 tokens. So we've got token, we've got eyes, followed by a space. And often it's the case that substring followed by a space is a distinct string from substring, and me followed by a full stop. Different tokenizers might do this differently. They might like split the full stop out as a separate thing. All of these are sort of implementation details that seem, to be honest, fairly arbitrary. And then we have a vocabulary of some large size. This is typically tens to hundreds of thousands of distinct possible tokens. And so I've again invented that the token is vocabulary entry number 580, eyes space is 123, and me dot is 44. And then the way that we embed these tokens is we have this large embedding matrix. And this embedding matrix has a single vector for every element of the vocabulary. And so each token gets a vector. So we've got our embedding matrix, and we just take the 580th column, the 123rd, and so on. And this will just, and this is the first of the trainable parameters in the language model. This is the embedding matrix. We've taken our tokens, and each token has an embedding vector, and then you get a series of tokens in kind of time order or sequence order. So is that bit clear? Yeah.
Can I ask how does it deal with the tokenizer when there's like an overlap between tokens? Like if they're not orthogonal, kind of like I was just thinking ahead of an example. If it was like not and nothing.
Yes.
And yeah.
Depends on the tokenizer, but typically it will try and get the longest.
Okay.
The longest token that it can.
Okay. Yeah.
And because the reason is that training tokenizers usually start out with a very minimal vocabulary, which might be like all the letters and punctuation and that sort of thing. Like you typically have a vocabulary which any possible input can fall back to, or in the case of the OpenAI, when you have like a byte, you have all the possible byte pairs, your initial vocabulary. So like,
yeah.
So rarely encountered words will get loads of separate tokens, but frequently encountered words will become one big substring as a token. Cool. Okay, so that's how we get the vectors in the first place. Now we have a series of vectors. And what do we do with them? Well, we put them in a box. The box is the transformer. And we've got token 0, token 1, token 2, and we're going to predict the probability. We're trying to maximize the probability of the true next token, given the tokens that have preceded it. And that's typically referred to as the context or the prompt or whatever. Those are used sort of interchangeably. So this is not terribly useful. Maybe it's not like a box, it's like a series of tubes. And we have one, two, so you've got one processing element for each at each token position. This wouldn't be particularly useful to structure it this way. The reason for this is there'll be here, you've got token x2, its vector goes in, and you can use that to predict the next token. That's not terribly helpful because this can only learn bigram probabilities. So all the information that might be latent in x1, token x1 and token x0 is being discarded. So what we need is some way to pass information from one token to the next. And the kind of old language modeling paradigm based around recurrent neural networks would do it in this way. You maintain some state, you update that state based on the vector that you've put in, and you carry that state forward to the next position. So you can't get from token 0 to token 2. You can't pass information from token 0 to token 2 without first passing through the state of token 1. And this was quite successful, but, and it's good because it can model arbitrary sequence lengths. But it has the disadvantage that empirically it's very hard to learn long-term, like long-range dependencies with this. And you can sort of see that because although we think of depth as running kind of from the input to the output, if you imagine, well, going from x2 to the next thing, next token has like depth 1 here, but going from x0 to x2 has depth 1, 2, 3. You know, the long-range dependencies correspond to kind of much deeper neural networks, and deeper neural networks are generally harder to train. So what we really want is a way to sort of skip arbitrarily forward and pass information to tokens in the future. And that's what self-attention does. Sort of, if you have one intuition about self-attention, your intuition should be, it's a way of moving information from one sequence position to another without having to go through intervening tokens. Okay, so I'm going to talk through this diagram here. I've sort of opened this up and diagrammed out all the different little subcomponents of the transformer, and then we'll go through them all in detail. So our tokens go in, and then we have this orange block here is the attention block. Oh, sorry, this whole thing is called a transformer block, and this orange bit is the attention layer. Our token goes in. Attention can process information from previous token positions, pull them in, and contribute it back to the embedding. And then we have a multi-layer perceptron. I'll go into that in a second as well. We have a multi-layer perceptron that acts locally to each token. And that, again, adds its information back into the representation. Don't worry if that seems very high level. We will go into the details of these in a second. But there's essentially two components. There's attention, pulling information from previous locations, and there's the perceptron, which is processing information locally to the token. Some people find it useful to think of this in terms of having like a multi-threaded program with a different thread running at each token position, and the attention being a way to have cross-thread communication. If that's a useful metaphor, take it. If it's not a useful metaphor, then just like forget that. So that's one transformer block, and then we just repeat this d times for a network of depth d. Okay, so now I'll unpack what I said. Yeah, I'll unpack the individual components, and this is the self-attention component. This is sort of the technical crux of this talk. If you remember, like one bit of details, like try and remember like the next 5 minutes. That will probably be like the best value for attention in terms of this talk. Why do we need to have self-attention? Basically, in order to extract information from context. So imagine that we've got the context. Alice, maybe it's a story about someone called Alice, and then there's some intervening text, and then there's a woman named, well, intuitively, you're probably going to say Alice, and that seems like a reasonable prediction. But how do you actually reach this prediction? Well, we've got vectors to deal with, great. So now that we're at the token named, we can know a few things. It's probably going to be a name, but also we can do better than, like, it's probably going to be a name. In this case, we might want to like bind to a specific instance of its name, Alice, and use that information to predict that it's going to be Alice, rather than say rather than like just saying, oh, it's a name. I'm just going to use the base rate of names across the whole corpus. That's not, yeah, we can do a lot better by looking in the context and saying, which name have we seen? So the Alice, so hopefully the Alice embedding here will have, if the network is working well, the Alice network will have some sort of component that will say essentially like, I'm a name, pick me. You know, this is where you should go for information about names. And then we can pull that information across. Yeah, good. So how does this work in practice? That's the sort of, what is attention meant to do? What's the kind of design philosophy behind attention? And now I'll go into how it actually implements that in practice. So there's two parts essentially to the attention algorithm. One is weighting, which is a way of saying which tokens do I want to attend to, and the other is value vector creation, which is saying what information do I want to pull from those tokens. So we'll talk about the attention weighting first of all, because this is the kind of the bit that I think is the most confusing. So we'll go slowly, and please, like, this is I just want to reiterate, stop me when things stop making sense. This is the most confusing part of the talk. Just emphasize that. So what we do is we've got our embeddings, and we apply two linear projections. We apply a query projection, which gives us a query vector. And then at each token position, we apply a key projection. So this is just matrix multiplication. We've got our embedding. We apply a matrix, we get another embedding. So we have a key for every position. And then at the position we're attending from, we have a query vector. So sticking with this kind of running example, if networks are not really quite like this, but hopefully this will make it a little bit clearer. Imagine the zeroth, like the 0th dimension as a 1 represented by this black square if this token is a name, and a 0 represented by this white bit if it's not a name. So then we'd want to have a query vector which has a 1, otherwise zeros, and this key projection should say, ah yes, I'm going to have a 1 on Alice and 0 everywhere else. And then what we do, we've got our query and key vectors we've achieved by doing these linear projections. These are more trainable parameters. We just dot product them. So if I want to get the attention weight from position 1 to, from position n to location 1, I just dot product the key vector from position 1 with the query vector at position n. So you might say this, you might be like, well, there's a lot of linearity going on here. There is a lot of linearity. There's an enormous amount of linearity in transformers. And the reason for that is that accelerators are extremely good at doing linear calculation, at doing like matrix multiplication. So this is one of these sort of hardware lottery things where this turns out to be good. You don't need to make it nonlinear. You can just do the quick thing. And then we do dot product to get the attention weight of position 2. We do the dot product again, but now there's a 0. So we've got a whole load of zeros. The dot product is 0. And we keep repeating this. And this gives us a scalar for every position. Okay, so we can aggregate these into a vector, which we can call the attention logits. Generally, if someone calls something a logit, it's because they're going to softmax it, and that's exactly what we do. We take the attention logits. These can be any values. And we softmax them to get attention weights. So softmax, in case you're not familiar, the softmax of a vector is you take the exponential of each element of that vector, and then you divide it by a normalizing vector. This is essentially the Boltzmann distribution, if that helps. And so this will give you a normalized vector of attention weights, 1 for each position. That was attention weights. Did that make sense? Cool.
I don't think that fully understood it. So you say the name is a verb, then you translate that into the noun name, and you say which of the properties. So next, Alice is holding a can. Now you have another word. What things could you possibly be holding? And so I'm not entirely sure I understand. There seems to be a lot of understanding on the side of what exactly the words mean. So how do you construct a query?
So this is where the deep learning works. Part of the intuition is now entering the picture. You don't. You just initialize these WQ and WK matrices with random values. And over time, they will hopefully learn to extract relations like this. And generally, they actually do a much better job than you might expect. So we're not kind of constructing them by hand. I was trying to give a very constructive example in order to kind of make the purpose clear. Perhaps an alternative way of saying this is that maybe is a bit more formal and more useful from that perspective is that you're kind of constructing a bilinear form. You've got the source token and the query. You've got the query and the key embeddings, and if you write it out, then you end up with the key matrix. So the key weights transpose times the query matrix. That gives you just a single matrix. And so you have a bilinear form, but it doesn't have to be. It's not a quadratic form. It can have asymmetric components. So you can represent kind of one-way relations with that rather than just, it's not, you're not constructing kind of a metric over token space. I don't know if that helped or was completely unhelpful and confusing.
No, I think that what you're basically saying that this works somewhere behind the scenes,
Mm-hmm.
and if I were to understand what it could roughly be this, but how it came to be there.
Yeah, and the question of how does it come to be there and what algorithms are actually learned, I think is like one of the main scientific questions that is really exciting. Like in my opinion, all of science at the moment. I expect people will disagree with that. We can talk about that later. Okay, so we've got our attention weights. And then the question is, what do we do with these weights? It's not very useful to have a single scalar. That doesn't actually tell you very much. Well, guess what? We do another matrix multiplication. So there are 3 matrix multiplications. This is the value vector. So this is the value matrix. We take the embeddings, we project them with our value matrix, and now we have a value vector for every token position. And all we do is we aggregate these with a weighted sum, more linearity. It's just an absolute ton of linearity. So the attention output, the output of this attention head at position n is the sum over the previous tokens of the value vectors weighted by the attention weights that we got through that dot product mechanism. Does that make sense? There's a few moving parts here. Again, like the purpose of this is that it makes sense to you, not that it makes sense to me.
Wait, the weights here, the omega.
So the weights are the omegas after they've been softmax. So it's just a normalized.
Yeah. Okay, cheers.
Cool. So now we have the attention outputs, and I slipped, did a little bit of sleight of hand. I said that that's the output of this head at this position. So there's 2 things going on. The same mechanism is taking place at all of the token positions. And turns out that actually we do this at multiple heads simultaneously. And a head is just a duplicated attention. It's just like a duplicate of the attention mechanism with a different set of learnable parameters. So we just, that was not so clear. So we have like, at a given layer, we have WQ1, WQ2, WQ3, and so on up to WQH, where H is the number of heads. Nick?
Just to sort of get an order of magnitude impression, how many tokens are there? So if you're doing some addition of your value vectors, some linear combination of them, how many are you talking about? Billions of these things? How does it work?
There are 3 senses in which I might answer that question. One is how large is the vocabulary of the tokenizer? How many distinct tokens exist? That's okay. About 100,000 ballpark. There's some, if you actually look at the vocabularies of things like the OpenAI tick tokenizer, there's some wacky stuff in there. There's some complete nonsense. So what is the correct way to token? But it's the example that you gave actually is quite good because there's a lot of special casing goes on in modern tokenizers as well. That's designed to help them deal with arithmetic, for instance. So you might take instead normal tokenizers do all sorts of funny things with numbers with commas in and that kind of thing. It might be like you find a number, you special case it to divide it into tokens for every individual digit, say. Yeah. Does that answer your question? Cool. Yes, of course. So how do you get them? You apply each query, you apply a linear transformation, and key, you apply a linear transformation. Value, you apply a linear transformation from the corresponding embedding. You might also be wondering, like, what is the purpose of the query, key, and the value? The purpose of the query and the key is to compute a weighting that says how important each token is going to be in determining the final answer. And the value is to use that weight. The purpose of the value is to take that weight and be used in a weighted sum. So you, the purpose of the value is the thing that will be copied over. And the weights are saying how much you should include it in the copying or not. So in this case, like, there's probably no useful information in the token A to the type that like there's a vector here, there's something, like we applied linear transformation, there'll be something. This vector will exist, it will have some contents, but the actual information contained in these vectors will not be terribly useful for the task of predicting the next token in this case, which is getting someone's name. So we want to downweight. Because we're applying the same matrix to each position, we kind of want a way to say, okay, you applied that matrix, but that's not very useful. So the value is the thing that will be copied. The query and the key produce the weights to determine how much you're going to copy. Does that answer your question? Cool, great. I think chap in the green shirt first.
I understand the query ends up having a vector that contains the information of what do you need next.
Yeah.
The key is that instruction information of what the key features of each word, each token, so that can have those for the words. And the value obviously is what just the idea behind the rationale behind multi is it more a parallelism aspect, or is it also to kind of have a richer vector representation of all those features?
Both. It turns out that one thing that I've not included in this is that actually you end up projecting down to a lower dimensional subspace. That seemed like a sort of one piece of information too many. So you can do it in parallel, so why not? And this means that heads end up specializing into different functions. And so the query matrix can be specialized for picking out like parts of speech or some. And I'm sorry, I don't know your name either in the blue shirt.
I think it might be a good question. If words like are irrelevant, but you're not telling it has to figure out on its own what grammar is, you're telling it what the pronouns and verbs and so on are. You would think that figuring out not to put in too many the or are around is very important for it to look human. So I guess it's asymmetric that is very important when predicting and not very important for the information for the next word. But it would be quite important that you need definitely to put it in the sentence, because otherwise you're skipping the article. Yeah. So how do you? So the art is not very important to the task of choosing the name, right? But if this were to instead be like some, then the next thing wouldn't be woman, it would be women. Yes.
So this is what I mean by like you're trying to get as much information into every single context contains tons of different tasks, multiple tasks at each token, sometimes multiple tasks at each token position.
I think my question is, does this imply that it settles for some or are at some point and then it's fine with the grammar, or does it mean that it's kind of iterative and then it will go back and see, okay, did I get, all of it right? Is there any grammar check, or does that just follow naturally?
There's no sense in which you can iteratively process apart from network depth. There's some evidence showing that like tracking how network predictions change with depth as you continue the forward pass. But all the iteration takes place internal to the model. Okay, so just to recap on what we were, we've applied multiple heads in parallel, and these will give us multiple outputs in parallel. But what we need to do is get back down to a single embedding vector for this token. So what we do is we concatenate them. Now we have a very wide vector, and then we apply another linear transformation. This gets us down to the correct dimensionality. Another little thing to sneak in here is positional encoding, which is it's a thing that people like to iterate on, but basically the idea of a positional encoding is that the transformers mechanism, there's nothing in anything that I've just said that tells you this is token 12. And this is actually a very useful thing to know, because at least you want to know if different tokens are next to each other to see if they're part of the same word. But there's all sorts of reasons why you want to know positional information. So, sure.
Multiple heads. So you have, let's say, the embedding vector of the original time is, let's say, 128.
Yeah.
And if I have, let's say, 2 heads, and I would have 64 dimensional per head.
Yeah. That's right. So I sort of, because I didn't want to rescale the graphics. This is sort of a little bit little bit wrong. These should all be narrower. It always goes to a lower dimensional space. And for reasons of computational efficiency, if you divide the embedding space, say you divide it into H heads, then the embedding dimension inside the embedding dimension inside the attention block will be, if this is D, it will be D over H. So this is coming back to an embedding of dimension D. And this is dimension D. Does that make sense?
Yes. Yes. What is the purpose of this WO? Like, matrix there, like it's just
don't know. This is formally equivalent to.
Because you think that you have been explained, perhaps it's absorbed anyway there.
Yeah, the right place. I think the correct place to think about absorbing it is absorbing it into V, because you can think of having just a like a column subspace of WO, which will correspond to some of the WV. There's a paper which I'll talk about this afternoon, which will make this much more formally precise, which you might find quite interesting. So the purpose of positional encoding is just to say to a transformer, this is token N. And what you do, there's all sorts of different types of positional encoding. People love to create different positional encodings. But you can think of it as a vectorized position signal. And you can either add that into the embeddings when you embed the tokens in the first place, or you can add it as a piece of side information to your attention algorithm. I think if you're aiming for an overview understanding, just think of adding a vector to the embeddings in the first place that says where you are in the tokens, sorry, where you are in the input. And the other thing, in order to actually extract some kind of useful learning from this, you want to make sure that if I'm trying to predict token at position t+1 at token position t, I can't just attend to the one in the future and be like, oh, it's that token. That's a completely trivial algorithm. So we use what's called a causal mask, which it's a very fancy way of saying, for all the tokens in the future, i.e., the suffix tokens, set the attention logits to -infinity. You're not allowed to attend to them. So that's what a causal mask is. People get, it sounds fancy. It's just a way of saying, like, don't do the trivial, silly algorithm. Okay, that was attention. That is how an attention layer works. Hopefully, this has been useful. Now it's sort of all downhill from here. So first, the sort of next bit downhill is the multi-layer perceptron. This is the thing that happens per token. So you have the kind of vanilla design of multi-layer perceptron is very simple. We have our input embedding again. We apply a linear transformation. We go to a higher dimensional space. This gives us what we call pre-activations. So these are just a linear transform of the inputs. Then we apply some non-linearity to get the activations. And then we project it back down. Great, that's it. That's an MLP. It's a single hidden layer perceptron. And, oh, that's a bit tiny. So the only real elements of the design space here are how big do I make this internal dimension, and what non-linearity do I apply? People love coming up with different non-linearities. In practice, people use, sorry, you can't read those. They use the ReLU and the GeLU. ReLU is like this, it's 0. It takes the input, and the output of a ReLU is max 0 and the identity. So essentially, if the input was negative, it's set to 0. Otherwise, you just keep it the same. This works very well in practice, which is surprising given that it's not even differentiable everywhere. But it does have a pretty substantial problem, which is that the derivative is 0 when the input is negative. And so this leads to a phenomenon called like dying ReLUs, where the neuron becomes 0 and then it just stays 0 for all inputs. And this is just a waste of capacity. So instead, we come up with GeLU, which has non-zero derivative almost everywhere. So this generally gives you a few % bump in performance. You make better use of your capacity. I include this just so that these things, which are this sort of mystifying jargon, you just know ReLU is like that, GeLU is like that. But you should, if you want a simple mental model, just think of the ReLU. And another sort of quick jargon busting thing, a gated MLP is much like a regular MLP, except instead of one projection, you have 2. you then apply a nonlinearity to one of the projections, take an element-wise product. So that's why this is like a gate for this one. And that gives you something you project back down. This is probably the least important thing. So if that all seemed a bit mystifying, that's okay. I just include this so that when you see gated, like you see GEGLU, it's a MLP with this gating mechanism. Don't really worry about it. It's quite simple. You can refer back to the slides and reassure yourself that you do actually know what a gated linear unit is. I also included this because I wanted to include this paragraph from the conclusion, which is sort of periodically people rediscover this paper and this conclusion, which is quite, maybe you can't read it back. It's, we offer no explanation as to why these architectures seem to work. We attribute their success, as all else, to divine benevolence. And that's sort of the theme of transformers. Another bit is the residual connection. Yeah. This one is typically 4 times higher dimension. Why? Because that's what people did a sweep, and that's what worked best. It works, but it works worse. Okay, so residual connections. When you hear residual connection, this is what it means. People, sort of in the bad old days, we used to have neural networks like this. You have the activations of one layer, you apply some function, or whatever, and then the activations of the next layer, just the function, just that layer applied to the previous activations. With a network set up like this, as the network gets deeper, it becomes much harder to train. So there's one simple trick. You add an identity. This is a residual connection. This is called a skip connection. So now the only thing that's changed is the activations at one layer are the activations of the previous layer plus the application of the intermediate layer. It's very simple. That's all a residual network is. It makes a huge difference in practice. And one other thing that I sort of, in order not to scare you, I kind of snuck in is normalization. I think I'm actually going to skip the details of normalization, but essentially what's going on is you are centering the activations. There are various different ways you can center them. The one that I think is conceptually simplest and doesn't seem to have any performance penalties called RMS normalization. All this does is normalize your activations to have Euclidean norm 1, then apply some per neuron scaling vector. So project it to the sphere and then just rescale each element. If you don't do this, your networks will struggle to train. I don't really like it personally, but have to live with these things. One other important thing is, where do you put your normalization? Just put it here. Put it before the input to the layer. Normalize inputs, don't normalize outputs. Empirically, it does much better. That's if you're writing neural networks and you have a residual, you have a kind of residual network, put your normalization on the inputs. If in doubt, put normalization everywhere. But if you're going to push it anywhere, push it on the inputs. Sorry?
How do you compute the normalization parameter?
Oh, the sigma is just the root mean square of the activation vector. No, batch normalization is absolutely cursed and you should never use it, unless you like bugs. No, batch norm does work, I just hate it. But how do you actually compute it? Well, you have a vector. You have the embedding vector. You take the norm of that vector and then divide every element of that vector by the norm. So you're just making RMS norm just changes your embedding vector to have norm 1 before applying element-wise rescaling. The element-wise rescaling is learnable. I don't know if people have tried getting rid of that. It's always a good idea with deep learning to be like, what happens if we get rid of it? But, okay, to recap, our transformer consists of inputs which have been tokenized, residual connection with attention, residual connection with MLP, and prediction. And we repeat this d times for a network of depth d. One thing that I really want to emphasize is just because a attention layer attends to a previous token position does not necessarily mean it's using the information specifically about that token. You can have something like this, where this attention layer has pulled information from token position 0 and added it into the residual stream at position 1. And then this subsequent layer has pulled it from position 1 into position 2. Does that make, yeah, Nick?
Just for clarity, so you've got your linear transforms, things like MQ, and you want to index them by the layer. So you're learning, if you've got D layers, you've got D
times H, the number of heads. Yeah. Okay. Quickly talk about training. We train on the log loss, which is just negative log probability of each token given the preceding tokens. And the nice thing about transformers is that every forward pass gives us T contributions to the loss. So they're quite efficient to train. And the training setup, this is one of these things that people used to think transformers were quite hard to train. Essentially, there's two things that make training work. One is a linear warm-up. So you start at 0, you go up to your maximum learning rate value, and then you decay with what's called a cosine decay. Now, the actual values of these hyperparameters are a closely guarded secret. Like these training runs cost tens of millions of dollars. You get the hyperparameters wrong, you've just blown tens of millions of dollars. So people care about getting them right and care about their competitors not knowing them. Another thing that's really important for your intuition is that training is basically always one epoch. So you're not repeating data except by accident if you fail to deduplicate your training set correctly. People worry a lot about overfitting, but training for one epoch is much harder to overfit. And then sampling, the sampling mechanism is that you have a probability distribution, you sample from that, you append it to your prompt, and then you sample again. So this is autoregressive sampling. When I say an autoregressive language model, it just samples next token, append it, and try again. And there's a few kind of buzzwords that you want to know when you say go onto the OpenAI website or sample. You'll pass like arguments to their API. Temperature is essentially adjusting the entropy of your distribution. The top K sampling takes the top K tokens ordered by probability and only samples from that appropriately with the probabilities renormalized. And top P does something which I think is slightly better, which is it takes enough tokens to have probability mass, at least P, and samples from that distribution. So that's for variable size. Okay. The conclusion for now, because we've got to talk this afternoon, is we've covered language model foundations, like why people train them in the first place, what they're trying to achieve, what's the architecture they use, what's the training setup, and how do you sample. This afternoon, I'm going to talk about scaling laws, evaluation, interpretability, and alignment. So see you there. And thank you. I'm afraid this has taken longer than I planned, but hopefully there's some time for some questions, or I'll be around at lunchtime. Thanks. Go ahead.
Why we need MLP after
one answer is the usual unsatisfying answer of people try loads of architectures and this is the one that worked best. A more substantial answer is that attention is it's not a particularly complex calculation. Essentially all you're doing is applying a bunch of linear transforms. There's very little non-linearity in it. And then there's also a paper on like attention losing rank with depth. So if you have an attention only network, as it becomes deeper and deeper, it essentially becomes more and more useless. I can't spell out the technical argument there, but if you look for attention loses rank doubly exponentially with depth, you'll find a paper that will answer your question, hopefully quite satisfyingly.
There's no non-linearity.
There is just the only non-linearity that you're getting is the softmax from the attention logits, that are the per token logits, to the per token weights. Is that correct? Yes, that's correct. Okay. So, what I'm trying to do today in this half of the talk is more of a kind of, hopefully I've given a decent explanation of how language models work. or at least like the architecture and how we train them. Now I'm going to try and build on that and talk about some cutting edge topics. This is pretty opinionated. There's other things which I think are tremendously important that I'm not going to cover today. We're going to cover scaling laws, evaluation, interpretability, and alignment. So that's, these are the kind of buzzwords you might have heard, unpack those a bit. There's other things which I think are really important and interesting. Like performance and optimization. If you have a background in engineering or you have a background in systems or computer science, there's potentially huge opportunities. Data sets, I think we don't understand nearly enough about what we're putting into the models and what effect that has. Long context and retrieval. Reasoning is kind of the holy grail at the moment, and multimodality. So that's like you take your language model and you kind of jam a vision model on the side, one way or the other. I think this is, these are all things that are hot industrial topics. And I think if any of those sound interesting, I can give you pointers to them. And the other thing that I want to achieve is I want to learn about connections to your research. So if any of this kind of sparks something in mind, you're like, I think that kind of approach makes sense in my field, or that reminds me of something from my field, then I want to hear about that as well. And questions, clarifications, etc. Earlier I was aiming for like understanding. You should go away being able to actually understand self-attention. Here I'm just sort of giving you pointers, and hopefully you'll get a bit of a flavor of what's going on. The aim is not that like you have like a download the deep understanding of 4 separate fields to your brains in 45 minutes. I don't think that's possible. So clarifying questions during, broader questions afterwards. Please bug me if I don't share slides. Let's get started. So scaling laws. Scaling laws are kind of the thing that powered language models. Well, why are large language models large? Because we find that when we keep scaling them up, they keep getting better. And what I mean by this is we've got some performance measure, and we increase the compute that we spend. The scaling law tells you how much better you can expect the model to get as you increase your compute spend. So just to introduce some handy notation, perf being our performance measure, C being compute. So this is like the kind of modern scaling laws. There's an asterisk here on first because people, as with more or less everything in modern deep learning, people also did it in the 90s and we just forgot to cite them. But the first scaling law about transformers and modern language models is this Kaplan et al. Paper. And the performance measure we're using here is test loss. This is just a holdout set from the same language training corpus, which is basically a scrape of the internet. And compute is on the x-axis. So perhaps this might seem a little strange, but the question is always, I've got these GPUs or TPUs sitting in my data center. Like, how can I get the most value out of them? How can I get the best model out of them in the time that I have available? And for scale, the NVIDIA H100 is kind of the modern top of the range accelerator that everyone's currently fighting over. That has an approximate throughput of about 4 petaflops. Flop being a floating point operation, peta being, I think, 10 to the 12. Excuse me. So the x-axis is measured in petaflop days. This is back in 2020, and you can see that we're almost off the right-hand side with just one accelerator now. So like accelerator technology has moved quite fast. But it's worth keeping that sort of scale in mind for other plots which have compute on the x-axis. So the way that we get scaling laws is that we take training run loss curves. This is test loss, and each individual light blue line, like here, is a loss curve, and we plot them all on the same plot, and we compute the efficient frontier. And what I mean by that is, for any given value, say we just take the lowest value of loss achievable by any model in that set. And you can see that what happened, and when you plot this on a log-log plot, you get a straight line. So we have a power law. So we get power law scaling in test loss as a function of the compute that we spent on it. That is basically the heart. That's when someone says scaling laws, this is what they mean. You have compute on the x-axis. You have some performance measure on the y-axis, and it's probably a power law. If it's better than a power law, congratulations, you've like literally just won the lottery. People try and beat power law scaling. It seems almost impossible. to like beat power law scaling in a sustainable way. There's all sorts of theoretical explanations for this. I'm not going to go into the theory, but if anyone is interested, then let me know. I'll send you some pointers. I think the question people tried to explain it, I think really it's kind of the jury is still out as to exactly why it should be power law scaling. But there's a sort of more superficial explanation for why we get scaling laws at all. And that's because scaling laws come from a trade-off. This trade-off is between the cost to process a given datum and the amount of loss reduction you get from the typical datum of your data. This one on the left, this plot on the left has tokens processed on the x-axis, test loss on the y-axis. Model size is indicated by these are the biggest models, these are the smallest models. So you can see in terms of data efficiency, the large models dominate, just like strictly dominate small models in terms of data efficiency. But they're so slow to run compared to the small models that this model has finished training, like literally before this one's even done its first data point. And by finished training, what I mean is its losses essentially plateau. Sometimes they will slow down a little bit, and people sometimes train for a really long time to get models that are comparably small, but it's incredibly inefficient to train once your loss starts going down like this. Excuse me. What's happening is that the fact that models plateau means that once your model has started to plateau, if you're going to spend more compute, if you're going to spend compute that was going to take you along the plateau, you would have been better starting with a larger model. Does that make sense? This is kind of the core insight of scaling laws. So I want to make sure that this part makes sense. Okay, so that's the scaling law, and everyone was really happy. Line goes up, amazing. Rocket to the moon, etc. Laser eyes, and so then we got the GPT. This was just after GPT-2. This is the GPT-3 paper, and I saw the scaling laws paper, and I was, in some sense, I was like right about it. I was like, yeah, there's a line in the graph, the line will continue, but in an important way, I was totally wrong about it. The way that I was wrong about it was what this change in loss would actually correspond to, because the test loss goes down. You might think that when the test loss goes down, well, it can go down for lots of different reasons. Maybe it will just, make better spelling mistakes, or it will do something else that's like some superficial and uninteresting phenomena that is still the most efficient way to decrease the test loss on the margin at the moment. But in fact, what happened was that it turned out that when the loss goes down, this actually corresponds to economically valuable things. GPT-3. Unclear to me. No one's really saying whether it was actually profitable or not. Certainly there are whispers that it was like making money. Probably GPT-4 is making money, but there's certainly the potential for economic value in the stuff that was learned between GPT-2 and GPT-3 and so on. DeepMind got in on the act. Another thing. It's like these author lists are just massive. Some of this is like courtesy authorship, but a lot of it is these people were really actually involved in training the model. Like these author lists are huge because these are large, complicated code bases, because they are hard to train. It's hard to do the engineering to train them. It's hard to analyze them and that kind of thing. So there's a sort of organizational lesson there that I think we could unpack later. But then the wheels kind of came off. And I remember this period being like, there's sort of whispers going around the cafeteria, like, oh, we've fallen off the scaling curve. It's like, we're not quite on the scaling law, what's gone wrong? Certainly models, but we were not getting the results out that we hoped. And I think that was true for the entire field. What had happened was something a little bit subtle. So scaling laws, although I could describe them as perf of C, in fact, if you've done any amount of machine learning, you'll know there's all sorts of hyperparameters. And if you get these hyperparameters wrong, then your model will be like somewhat or drastically worse. And as you change your compute spend, you change a bunch of these hyperparameters. Some of them you change trivially, like you change the amount of data, or you change the model size, simply in order to spend more compute. But some of them you change, like the learning rate schedule. If you get the learning rate schedule, that will need to change as a function of model size. And if you get it wrong, if you get your hyperparameter selection for a given compute size wrong, then you will fail to scale as well as you could. So essentially, a large part of keeping yourself on the scaling curve is getting this like hyperparameter set of C, is getting your H of C scaling right. You want to make sure that you're actually getting your hyperparameters correct. Otherwise, you'll gradually get worse. And this, unsurprisingly, in retrospect, is what happened. Sorry, this has actually come out smaller than less legible than what I expected. The original Kaplan scaling laws paper, they trained their model for less, they got their data set size estimates by taking results from the middle of training as opposed to training the model for a given data set size. These two things are subtly different because if you get them from the middle of training, then you'll use a different learning rate schedule, which means that your mid-training model will be suboptimal. And so what happened was that they ended up with a sort of overestimate of loss at small data sets, which made them over-optimistic about how the model would improve when the data sets got larger. But unfortunately, this actually didn't happen. So then DeepMind, there's this chinchilla scaling is where what happened when DeepMind figured out that you should did the analysis correctly, basically. That sounds a little bit patronizing. It's actually quite a hard and expensive analysis to do. I think the original Kaplan paper was like quite visual. So I don't want to, when I say like they did the analysis right, I don't want that as like Kaplan et al. With a bunch of idiots. They actually did an amazing thing. But then this sort of fine-tuned that relation. And when you do the analysis right, it's worth reading the chinchilla paper. You get the chinchilla scaling laws, which are essentially scaling laws for model size and data with different parameter values from the original scaling laws paper. And chinchilla scaling implies do a smaller model for more data, and you scale data set size approximately proportionately to model size. Previously, it was thought that you scale your model much faster than you scale the data. So these scaling laws, they look like smooth, essentially very smooth, regular phenomena. But there's a bit of a tension here against the sort of idea that models can do new things as they get bigger. So which is it? And the answer is perhaps a bit of both. There's this idea of emergence where more is different. And once you get past a certain amount of, past a certain model size, for instance, which corresponds to a certain amount of training flops, models improve their benchmark performance from being at random for all smaller models to suddenly much better, suddenly substantially better than random. This benchmark MMLU is a kind of multiple choice question answering benchmark I'll come to later. So we get in the grand scheme of things, overall smooth scaling. But when you look more closely at individual tasks, you often get quite discontinuous emergent scaling. And the same is true for sort of different abilities of models, like their ability to use a scratch pad to do addition, ability to use these sort of reasoning techniques like chain of thought, that kind of thing. So to some extent, models genuinely do seem to exhibit emergence. But there's also a question of, well, do they have this nonlinear behavior or discontinuous behavior just because you use a nonlinear or discontinuous metric? Like if you evaluate models on true, false, or like correct answer, incorrect answer by sampling, then you will get a discontinuous thing that goes from it's false to it's true. But if you were to evaluate, say, the relative log probabilities of true and false, you might get a smooth kind of interpolation. So it's not, the jury is still out. My feeling is that probably, unfortunately, unsatisfyingly, it's a bit of both. Like there probably are cases where models genuinely are getting new abilities with scale, but we're too quick to declare this ability was emergent. And in fact, to really declare something as emergent, you probably want to study it with all the possible metrics and account for sources of nonlinearity.
So is the way in which you would just sort of very roughly square this by saying you've got within your corpus, you've got your loss function, which is sort of moving more linearly, but some parts of your corpus, you've got non-linearity, where it's suddenly going on,
Yeah.
but because the onset of those different non-linearities is per subset, when you average over them, you end up with something that looks linear. Is that the sort of rough intuition?
That is the intuition that I have. And there's a very nice paper called The Quantization Model of Neural Scaling that goes into this a bit more deeply. I think that's a tremendous paper. And partly because it agrees with me. But like, I think it is genuinely also like very good. Yeah, I think that seems like the most likely candidate for how to square these two things, apart from measurement issues, which we can debate on any individual case. Okay, so that's scaling laws. Then evaluation. So there's the basic sort of evaluation where we benchmark. We have tons of benchmarks in natural language. This paper called Beyond the Imitation Game released a truly colossal set of benchmarks called Big Bench. That's worth, if you want like a single resource for modern language model benchmarking, Big Bench and its citation sort of graph is a good place to start. Then one that's really popular at the moment is this measuring massive multitask language understanding, which is that MMLU thing we saw previously. And this is all sort of reasoning, general knowledge, that kind of thing. It's essentially like, say, sending your model kind of to school and giving it a bunch of somewhat easy exams, some of them less easy. But, oh yeah, one thing that's worth saying here is that actually evaluations are not quite that simple to interpret. So this is doing a number of things. We're doing a multiple choice test here. How many numbers are in this list? 75A, 75B, 76, and so on. So there's at least two things being involved here. One is the ability to answer the question, and the other is the ability to successfully choose the letter corresponding to the correct answer, which is actually not trivial. Like, models are surprisingly bad at that kind of thing. So when you see emergence, sometimes what could be happening, one other possibility for emergence is like, there's multiple things you need to get right. And if you say that your model is able to answer this question, but is not able to select from the list, then you won't see it until the model also gets big enough to successfully select from a list. So that's one other way you can get emergence, when you have like a convolution of multiple different skills being required. And then there's also GSM-8K, which is a sort of benchmark that's seeing quite a lot of interest at the moment in reasoning, which is essentially grade school maths. Those of you who've been following the news maybe saw the OpenAI stuff about Q star. They were very excited about progress on maths. That's probably the benchmark they're talking about. So that's great if you can, and that's all benchmarks you can evaluate by essentially evaluating log probabilities. You evaluate the log probability of A versus B to do multi-choice. So
Just say wait if this is coming up, but like I assume those benchmarks are like massive things that everyone knows about, and they're all trained. All these models are trained on just massive amounts of scraped data. How do people make sure that they're not? So I imagine that benchmarks everywhere.
Yeah, I'll talk about contamination in a second. Yeah, I'll come to that. So then there's also benchmarks that are based on sampling. So these are providing kind of a Monte Carlo estimate of a model's ability because we can't sample all the possible strings. One example of this is this human eval benchmark code. And the way that this works is that we have our benchmark. This is a single element of the benchmark. We have a function stub, definitions and comments that specify what the function should do. Then you need to sample the function body. In this case, it's meant to turn a list with elements incremented by 1. So list comprehension, you sample that, and then alongside function stub, we also have a bunch of unit tests. So it's like leak code, right? If anyone's been on the job market, you're familiar with leak code. And if you pass all the unit tests, you get a pass on this benchmark element. And the number of benchmark elements you pass gives you the percentage score. And then there's also pass at K as another kind of bit of jargon that's useful. Pass at K means you're allowed K goes. And if any of them pass, you've passed. So in this case, maybe you sample the correct one, but you also sample something which is just not adding 1, you add 2 or something and you're wrong, but here you'd still get a tick on pass at 3. But things can be even worse. Like in this case, we have unit tests, and the unit tests are well defined, and you can evaluate them automatically. But lots of things don't have unit tests, like human preferences. And for this, we have to directly ask people. And what we've got here is a screenshot from a thing called Chatbot Arena. And you give them, you have a pair of models who have just chosen 2 somewhat at random. And I've asked them, write a neural network self-attention layer in PyTorch. And they come out, okay, written 1, this one's written 1, and I have to decide which I like better, or if there's a tie, or if they're both bad. And like, I don't want to drop out, so I'm going to prefer A. So we say, which one wins the comparison? This kind of preference data is extremely valuable because we use this for reinforcement learning from human feedback, which we're going to talk about later. But you can also use it for evaluating models. You can say this model is preferred to this other model, like such and such % of the time. And indeed, people do that. This is like one of the big leaderboards at the moment. They sort of turned it into a bit of a game where you have pairwise win rates. So this is like GPT-4 Turbo here on this axis compared to Claude 2 from Anthropic. And the number is too small to read, but you know, GPT-4 Turbo wins 71% of the time, say. So you have all these kind of pairwise win rates, which might be important if models sort of, one model is better than another at some specific thing. But you can also aggregate this in terms of ELO, which, you know, if you play chess or you play StarCraft or something you'll be familiar with, there's a kind of ranking score where the ELO attempts to predict the relative win rate, and a higher ELO gives you higher ELO indicates a generally more preferable model. Data set, so that's great, but a lot of these data sets are potentially now being trained on. How do you actually make it? If you've trained on a data set, it's pretty disingenuous to then say, oh yes, look at the great score we get in this benchmark, incredible. Contamination is generally pretty hard to verify for a number of reasons. Maybe you don't have access to the training data. Like I don't have access to OpenAI's training data, but also probably lots of people at OpenAI don't have access to OpenAI's training data. So if they wanted to check the data set contamination, they probably couldn't. And then even if you do, like how do you actually check? Like what do you actually use to check? If you use exact n-gram matches, so you look for substrings of length n, this massively underestimates things that if you eyeball them, you say that's contamination. And this problem is only getting worse because of the trend in using synthetic data. So people will, I think Microsoft's Phi 1 and Phi 2 models have been particularly criticized for this. Like they try and essentially distill synthetic data out, but you don't know if the synthetic data has been constructed with the test set in mind. Like that is definitely cheating. So there's an exact n-gram match wouldn't find synthetic data. I wouldn't find synthetic data examples, for instance. So there's lots of gray areas of what counts as contamination. I think the thing which is really decisive is like trying your model out on samples from the future. And one thing that people found was, I think, trying one of the GPT models on old LeetCode style problems, it did quite well. And then trying them on ones from the future, it did, well, not ones from the future, but ones that have been released since it was released, did quite poorly. So that kind of discontinuity gives you a sense that maybe those benchmarks have been trained on. A thing that you can include is a canary string. So this is like a 32-digit piece of like a GUID or something that you can look, that then when someone is creating their data set, they can filter for documents containing this canary string. And because it's just a random string, it won't be occurring in natural text. And they can drop those documents out. Or they can upsample them and get better benchmarks. Yeah, this is an example of, there's this GSM-8K benchmark. These ones have an alternative math benchmark score on the x-axis. They seem to be roughly correlated. These ones have an anomalously high GSM-8K score, their other math benchmark. So it's suspect. Yeah, their math scores are somewhat suspect. So like this is happening potentially in practice. It's not like just it's not just an academic issue. like probably you should be very skeptical of benchmarks, particularly when they're sort of commercially viable. Any questions here on evaluation or on scaling models?
I didn't quite get why. I understand for synthetic data that Ngram will work, but you seem very bullish about why it wouldn't hold in general. I couldn't understand.
Yes, sorry, that's something that only really makes sense if you've, only seems obvious, I guess, if you've done a lot of this, which is that a lot of really high quality tokens end up being derived from documents which were not originally on the web. So textbooks or something that you've got with OCR. Or they end up, basically a lot of really high quality things come from sources where minor formatting issues are quite common. And all you have to do is sprinkle in a few accidental new lines or spaces or that kind of thing to really confuse n-gram matches. But also the other thing that
just to check, I'm thinking it right. I've got like Dickens from scanned from library A and in plain text, and I've got Dickens scanned from library B and in plain text. There are going to be some heterogeneities.
Exactly.
Like edition 1 and edition 3.
Yeah, okay. Or different editions is another good example. You probably think that it's pretty matching, although I guess substrings would probably match there. There's all sorts of minor corruptions that can easily confound exact n-gram matches. And also I've done like embedding similarity-based lookups. And a lot of times you find something that it's not actually an exact copy, but it certainly changes your interpretation of the thing that of the benchmark that you're looking at. It's one of the reasons I'm very pro people releasing their training data sets, but that will never happen. Sad. So I'm going to move on to interpretability. This is something I've done some work on myself. So this is probably like, if you want this is probably where I can go the deepest. One of the kind of fundamental questions is interpretability research, even something that's worth doing, is whether neural network internals actually make sense. Like there are representations inside networks that correspond to the structure of the data that's being kind of fed into them, and also correspond to the way that we understand the world. So this example, like maybe there are neurons that activate for windows on cars or car bodies and car wheels and that kind of thing. And when you put these all together, you find a car detector as like one layer downstream. The question is whether this sort of thing exists in general. And a lot of the time in the past, people were like quite negative about that. There's this approach which is gaining a lot of popularity called mechanistic interpretability, which is essentially saying like, why don't we do neuroscience, but for neural networks? Why don't we why don't we apply the same level of effort and the same level of kind of scientific rigor and care to studying, say, Inception v1 or GPT-3 as we did on Drosophila. So I think there's other approaches to interpretability which are more kind of directly applicable, which aim to give you a quick explanation in terms of the input, like you can think of saliency maps. But this kind of mechanistic interpretability is largely what I'm going to talk about. But the first cut on like, do neural networks learn things that make sense is by finding things that we already know and kind of probing for them. So we just do supervised learning. We take the activation from some layer, we label the input with some concept, and we probe the presence of that concept with that. I'm afraid I'm going to do a shameless plug. This is a paper that I did on AlphaZero trained on chess. And on the x-axis, you can see the evolution through training. And on the y-axis, you can see the evolution through model depth. So we're essentially seeing the computational profile of the model as training goes on. And on the z-axis is hold out test set accuracy for that concept. So we used another chess engine to give us like 100 different concepts. And we probed for these concepts, and we found that we can understand like their learning trajectory over the course of training. And you get pretty strong agreement for a bunch of quite subtle concepts. Let's give it that for a second. And you can also flip it on its head and say, well, I don't know what I'm looking for, but I want to know what makes this neuron activate. And the way that you do that is by optimizing the input to maximally activate a neuron or a direction in activation space. And when you do this at different levels of a convolutional neural network, you get things building up from edges, through textures, patterns, parts of objects, and then whole objects. So these sort of maximum activating examples seem to provide another separate line of evidence that neural network internals are actually, at least in this case, fairly comprehensible. And you can do the same thing, but with data set examples. So this is a neuron which seems to be activated by, it's quite hard to see on here, but seems to be activated by things with a curved structure. And you can see the really negative activations are counter curves. They're curves going in the opposite direction. Then in the middle, you have completely unrelated stuff. It somewhat activates on, curvy-ish things. And then the really activating things are curves, the same orientation. Oh, excuse me. But this story gets a lot more complicated. And the way that it gets more complicated is through a thing called polysemanticity. And what this means is that when you look across, either across the dynamic range or data set or maximum activating examples for a given neuron, sometimes you'll see it just responding to a single clean concept. But sometimes what you'll see is this, like this example here, where this seems to be really highly activated by cars and cats and foxes. And it's not that there's something, there's not like some deep commonality between cats and cars. It's just that this turns out to be a more efficient way to represent concepts, because say you only have 256 channels in your convolutional network. Well, there are probably more than 256 things that you need to represent in the world. So you have to live with a certain amount of interference. And the way that you do this is by having almost orthogonal vectors. And in high dimensional space, you can get away with a lot of vectors that are almost orthogonal. So rather than in a d-dimensional space, you can only have d actually orthogonal vectors. You can have, I think it's x d squared, almost orthogonal vectors. And there's some parameter in there by how you measure almost orthogonality. So what that was a little bit abstract. The way this actually turns into networks representing multiple concepts across the kind of dynamic range of a neuron is quite well illustrated with this. So say that we're trying to represent five different concepts, and we take this neuron's, we take this axis to be neuron activation, so activation of neuron 1, activation of neuron 2. Well, as we scan through the dynamic range, first we'll pick up examples corresponding to this feature, and then we'll pick up ones corresponding to this feature. Then won't really be anything. Then there'll be ones corresponding to this feature and this feature and this feature. So this will look like a neuron responding to multiple different things. But in reality, there are multiple different, almost orthogonal vectors. I think this is a little bit subtle. That there's a paper called Toy Models of Superposition that will make this a lot clearer if this kind of analysis is something that's interesting to you. There's a lot of good theoretical work going on at the moment.
In the example you just talked through, you're saying that in 2 dimensions you can separate 5 concepts. Is that the basic idea?
You can almost separate.
Yeah. That's the idea.
Yeah. And the greater the amount of interference you're willing to tolerate, the more you can get away with packing more in.
Yeah.
And the thing that makes this work is also like features being sparse. Like if these 2 features always occur, then you should not pack them in like this, because when this one is active, this one will also be active. So feature sparsity is another major feature. So there's various different approaches to lifting this kind of polysemanticity. I think actually trying to discuss these is probably a bit too deep in the weeds, but it looks like this is not an inherent feature. This is not like an unsolvable problem. There's a recent paper on using sparse autoencoders to do this, and I think it's quite promising. Another, like the kind of headline results in interpretability has been this idea of induction heads. And induction heads are an example of a model learning an algorithm in its internals rather than memorizing specific things. So an induction head is a two-layer phenomenon where the first attention layer moves positional information, and then that tells the second layer where to attend to. So these allow the model, induction heads allow the model to kind of copy arbitrary strings. And these were discovered using interpretability. And they actually seem to be a real phenomenon that corresponds to a bump, like to a macroscopic bump in the model's training curve. So this is like a learned algorithm as opposed to a memorization that we found with interpretability research and actually occurs during training and has like a macroscopic effect on the model. So I think that's pretty cool. And then finally, the last part of interpretability that I think is like really pushing into the future is getting models to interpret themselves. So here you have, say that you found a neuron that you think is meaningful, or you've done your, you've managed to get around polysemanticity, and you've found a direction that you think corresponds to something meaningful. Then you still have the problem of like, well, we thought we had just like billions of the things, but fortunately we have a language model and it can tell us what they mean. And this approach seems to work somewhat. You give the model a piece of text, and you tell it how much each token in that text has activated a neuron, and then it tells you what it thinks that neuron is about. And this works somewhat. They don't really do a good job with polysemanticity, which I think will improve their results a great deal. And then the final thing that I think is a direction that was initially promising, but it's running into some difficulties, is trying to do like artificial neuroscience by ablating individual parts of the model. So this is an approach that's called causal tracing. What we get is we run the model, we get it to do something that relies on factual information. In this case, we're completing the context. The Space Needle is in downtown. The answer is Seattle. We guess the correct answer. But then we chuck a bunch of noise in the embeddings here, and that breaks the computation. So this is called the corrupted run. Then the intervention that we do is take a state from the clean run and patch it to the corrupted run, and then let its effects kind of run on through the rest of the model. So we make a single intervention and let its effects propagate forward. And what we do is we look for combinations of token position and depth that actually fix the output of the model. So what this corresponds to in statistical language is we're looking for mediators in the compute graph. And really surprisingly, they actually exist. You might think that there is sort of super distributed computation where no particular node is actually the node. But really, you can go from almost totally broken to almost totally fixed with a single patch. But this, I'm going to plug my stuff again. Sorry. This struggles with issues with multiple causes. Like you're looking for a single mediator. Well, if something has two causes that are synergistic, then you will fail to find it because you patch one, the other is absent. So what you might do is kind of work back by doing progressive ablations. You start from a fully intact model and you keep ablating. Unfortunately, when we were doing this, we found a really surprising effect where this is model depth, and this is the effect of a layer on the correct output. Where when you ablate one, the effect drops to 0. Unsurprisingly, that's why it's an ablation. But the effect of another downstream layer just kind of takes over to compensate. So this really complicates trying to do this kind of progressive ablation strategy. We call this the Hydra effect, because when you chop off one head, the attention head takes over. So as a result of that, I'm a bit more skeptical of whether causal interventions in interpretability really tell us that much about model structure. And then finally, we talk about alignment. So when alignment is this huge topic, people call it like AI not kill everyoneism. I'm going to keep it very technical. Be like, how do people make chatbots out of their language models? And the main approach that people use in industry at the moment is reinforcement learning from human feedback. Now, in normal reinforcement learning, you have an agent which takes observations from the environment, does actions, it gets reward. But we want the model to maximize what we want, and we can't programmatically like specify what we want generally. Like if you could write down a program that specified everything you want in life, your life would be pretty simple. So instead, what we do is we get human feedback. We use this to train a reward predictor, which will say, is this outcome, is this like state of being good? And then we use that reward predictor as a source of reward. And this is designed to get around the problem that human values are hard to specify like programmatically as reward. Instead, we just train a model. We optimize that. So for language models, this process essentially, we take the reward model as a fine tune of a larger model. We lop the top layer off and replace with the scalar predictor, which says this is good. And we do this using preference data. And then we train the fine-tuned language model, again, by starting with the base model, which is just the one that's come out of our pre-training run, and training that with reinforcement learning using the trained reward model. Now, preference collection and aggregation is pretty hard. Like, there's a lot of social science in here that I'm just not very good at, and I think the industry as a whole somewhat struggles with. So people try and come up with alternatives to RLHF, which is reinforcement learning from human feedback, because RL is generally incredibly painful. Anyone who's done reinforcement learning has probably suffered and cursed the name of reinforcement learning quite a lot. But also, just optimizing your learned reward is quite bad because you're essentially looking for flaws in your reward model. And so it's quite hard to actually do the correct amount of reinforcement learning. And it's also just a tremendously complex setup. Like the code bases end up being horrendous. So people work on alternatives. These alternatives are like pre-training with human preferences. So we take an existing reward model that we've got from somewhere, and we just use that to add some side information to each token, which is like, this is a particularly bad bit of text, or this is particularly good. And then we can train conditional on these tokens, this control information. So we also want to go beyond reinforcement learning from human feedback. One of the reasons for this is that it's actually very hard to do for complex tasks. So say that you're given a huge piece of text, and then you're given a summary of that huge piece of text. You know, asked, is this a good summary? Like, if you tried to do this, you can do it, but it's time consuming and error prone. Or if you're asked to evaluate some reasoning, it's quite hard to actually evaluate an entire long reasoning process. So what we do, one approach to this is called process supervision. And OpenAI and DeepMind both worked on this. And for this, we train a reward model that goes kind of per step in a reasoning process. So here we're evaluating every single step of the reasoning, rather than just was the answer good or bad overall. So it's much more granular feedback, which makes credit assignment a lot easier. And then this generally works much better for large and capable models. And the other approach that people are quite optimistic about is debate, where you get models to articulate two different points of view and kind of argue between the two of them as to which of these is better. And this output is provided to a human judge. And the idea is that the human judge doesn't have to see very much information. The model might say, this is the crucial bit of information. And then they'll be able to judge this long, complex reasoning situation without actually having to understand the whole thing, because the model will isolate the kind of crux point for them. And so an example of this in practice is, say you've got two players. One is trying to convince a judge who doesn't get to see the image. They only get to see one pixel that's revealed at the end. The player in red is trying to convince the judge that it's a dog. The player in blue is trying to convince them it's a cat. So they're saying like, here's a long floppy here. No, it's a cat. So that's his first box. It's a long floppy here. A dog. If you have to see that, it's probably a dog. But then if you just look at this bit, it looks like a cat here, and so on. And the debate process goes down to identifying a single pixel that proves the case. And these debates would ideally be very long. So the question that a lot of people in alignment were quite optimistic about this, and then there was a lot of questions like, does it actually work? The answer was like, no, probably not, unless you have, but the most recent results seem to actually be pointing in favor of it working, so long as you have like very long arguments with very strong models. All the things that have said debate doesn't really work have been really short debates where you don't actually get down to any kind of real crux of the matter. Okay, so this has been a sort of whistle-stop tour of all sorts of things. Like I said, these other topics I'm not going to cover. Andrea Karpathy has a really good talk if you want to hear a bit more about some of these. And we covered today, it's been probably quite full on. We covered foundations in the previous talk, scaling laws, evaluation, interpretability, and alignment. I'm going to put these slides online. Email me if I don't, or if you want to discuss anything. That's my email address. And I want to just close by saying, reiterating what I said right at the start, which is like, I think this is really an incredible time. There's this sort of new class of systems coming into the world, and we don't really understand them. But for scientists like us, that's a huge opportunity. There's potentially a new science that's being born at the moment. So, for me, it's very exciting. If you find any of these topics exciting, I'd be interested in collaborating. Please get in touch. Thank you. So I'll take some questions.
Yeah, questions.
The actual training of the parameters involving like keys, queries, is it that in practice you have a pipeline where you first train your model and then you have a second RLHF stage, or do you mix them both? And if so, how do you make sure that both signals, the one from RLHF and the one from key queries,
Yeah, so it's the same parameters. It's always the same parameters, except sometimes fine-tunes only use the last few layers. So it's the same parameters, and the pipeline goes pre-training, which is just take the internet and jam it into your language model with next token prediction. Then do RLHF with perhaps a subset of the parameters. But you're training the same model parameters each time. Anything else? Yeah.
I heard this word super alignment. What does it mean? Like, is it some advertisement, or what I basically understood is just like you're able to align even better than humans.
Yeah. So that's why I included the last few things, because this is sort of on people's minds at the moment. The idea of super alignment is that you have processes that would work even for superhuman systems. And that's why there's this emphasis in debate and in process supervision on dealing with evaluating model outputs that are too complex for a human to understand in their entirety. Now, the actual data sets and benchmarks that we're using, like grade school maths, I think I can understand that. Probably I can understand most of the questions in their entirety. But this is being used as kind of a proxy for reasoning processes that are too complex for us. Now, whether you think this is reasonable or not is another matter. Debate is an example of a proposal that is meant to scale to superhuman systems. Nick?
There's a nice paper on transformers introducing them by Turner. But is there are there any kind of like go-to introductions to transformers that you like or you want us to towards?
Marcus Hutter and Mary Fong have a very formal introduction. If you want every single thing spelled out, like the way that if you want like the mathematician or the RL theorist's introduction to transformers, that's Marcus Hutter and Mary Fong's one. Transformer circuits is quite good if you're interested in interpretability type things, but you also get along the way a very good understanding of how people think transformers, of like the transformer architecture and how some people think about its components. Yeah, that's what I would say. Yeah.
A lot of the evaluation slides showed GPT-4 is consistently like top right,
Yeah.
wherever, you know, best and best. And like, is it just bigger or like why? What's
No one knows. No one knows. Well, no, probably Sam Altman knows. If I had to guess, I would expect it's a mix. It's like a mixture, which is. So this is a total guess. I'm just making this up. I have no secret
more
information.
important than my taste?
I don't know. Like it's probably mostly the data, plus a little bit of training on the benchmarks.
So that must be like a massive commercial secret is how they train their data.
Yeah. And you know where they get it from. Like if it were me, I would hire people to literally write really top quality training data for me. Well, you know, if you consider the cost of hiring, say, a graduate student to teach you stuff, and the value of turning that information into knowledge that a language model can make use of, it's quite probable that trade-off comes out ahead, like for many graduate students.
And you would weight that data higher in the training. So,
yeah.
Yeah.
Well, you might. So you might. Ways you weight data higher is often by repeating it, which is not great. You could add a sort of weighting to the loss, but people typically don't.
Do that quite a lot in particle physics.
Oh, okay, interesting.
Weighted losses.
Yeah, I'd say probably the training data is where it's at. I mean, there's some whispers that it's probably a different size is a different type of language model, like it's some mixture of experts type thing. Which what I mean by mixture of experts is that where you have the MLP in the architecture, you have attention, residual, MLP. Instead of there being one MLP, there's like many. And you have some routing mechanism that says, oh, you're a token of type such, yeah, you're an embedding of type such and such. Go to MLP7. That's speculation.
Isn't that like a huge limitation to all this interpretability research? It's like if you don't know the underlying architecture.
Well, if you don't have the actual weights of the model, if you don't actually have the weight matrices and the activations, you can't do it. You literally cannot do it. It's impossible. You can't do interpretability research on GPT-4 without working at OpenAI. And probably many other people there can't do interpretability research on it, not because they're not capable, but because they don't have. Maybe they don't actually have access to the model. Like they can't run the model while looking at its weights and looking at its internals. That's where the sort of security perspective is at the moment. So yeah, that kind of doing scientific research on big models in big companies is maybe harder than you might expect for that kind of reason. Yeah.
Is it by just like a huge data set, changing the loss to change the signal which you want to train your model, like sentiment analysis or function structure or whatever?
Oh yeah.
Is it more something more deep at the structural and the architecture?
So for the preference reward models, those are the things that say this is like a 7 out of 10 answer. You have pairwise comparisons, and these you kind of back out a quality score, and you train the model to predict that quality score. And architecturally, this consists of taking off the top layer, the one that we're taking off the unembedding from, which would take you to the categorical distribution over tokens, and replacing that with something that goes down to a single scalar. And that scalar is like answer quality. There's no reason it necessarily has to be like that. you could instead answer, you could literally ask the model, like, how much do you like this? Rate it 7, rate it out of 10, and it will sample, and at some point it will, it'll give you like, I think this is a really great answer. I give it 4 out of 10, and you can be like, that's a stupid evaluation. And then you gradually train it to do better and better evaluations. So one sort of mindset thing here that I think people are gradually getting used to is to do less, and whether this is right or not, I don't know, but to do like less and less with architectural changes and more with just like literally write text that asks the model for what you want, and then write something to parse the output. Yeah, yeah.
Can I ask a technical question on the first half?
Sure.
It's about this residual training. And you said it learns better if rather than like z prime is f of z, it's 1 plus f of z.
Let me just roll back to that.
Is there any like obvious reason why that learns better?
Not one that's immediately obvious to me.
People say it's more stable.
More stable.
Yeah, but I don't know what this actually. So one possibility is that this means that f of z is always getting the same distribution of inputs. Sorry, f of z is always getting more similar inputs. Whereas if you, I don't know, I think this is one of these things where there's not really a satisfying explanation. There's certainly not a satisfying explanation that I'm aware of.
I think that does make sense, right? Yeah, it's like.
I think one explanation is that
Yeah.
Oh, the lost landscape stuff. Yeah. So that, if I remember rightly, that's switching from non-residual to residual. But perhaps I'm forgetting a plot in that where they compare pre and post normalization. But yes, I'd totally forgotten about that paper. That's like a good intuition for why residual training, residual networks are like a good thing at all.
Does it take longer to train? It's like stable, but it takes longer to learn these kind of like residual.
No, I don't think so. I think it is a pure improvement.
Okay. Yeah.
They're saying that. I know some people really want to get rid of residual networks, so there must be some downside that I'm not aware of. Or it might be like me with batch norm, where I just had this like dislike. I can't really account for it. Yeah.
Do you see any adversary attack like in computer vision for the NLP?
Not a topic I know a great deal about. Yes, to some extent. One of the reasons it's harder to do it's harder to do adversarial attacks of the same type that you do in computer vision, where you optimize the input, because tokens are discrete. So you could relax this by optimizing the prompt, optimizing the embeddings and then trying to project them back. You could do this by kind of jumbling up the input tokens, but there's no direct analog to optimizing individual pixel color values. But on the other hand, there's like the field of jailbreaks and that kind of thing, where you try and write text that gets the language model to do the naughty thing that its creators were trying to get it not to do. That is kind of very similar in spirit to adversarial attacks. Does that make sense?
But my understanding is that the NLP, you try to include very, very large text that's almost included everything. But for computer vision, you cannot do that. It's impossible. There are millions of ways to get the image wrong.
Yeah.
But for text, we typically follow certain rules. We speak on it, right? So in the sense that the larger the model is, the larger the data is, it seems like you don't even see any new things coming up.
Oh, like everything is to some extent in distribution. Yeah. Some people would say that's a feature and not a bug. I think I would tend to agree with them. But you can still come up with complete nonsense text. The question is exploring that search space in such a way that you will find the adversary. So probably there are adversarial strings. I think people will look for them, But the problem is exploring the search space is much harder than it is for images, because you can differentiate the inputs you can differentiate an image by changing the pixel color values. You can't differentiate a string.
I think I should pull things through. I let things run on a little bit because I wanted you guys to have a chance to talk to Tom, and also I assume the party was just being set up, but now is in full swing. So
Are we fashionably late?
I think perfectly timed. So thank you very much, Tom, again, really appreciate it.
Thank you for coming.